So for a large amount of my slot tonight, I'll be working over on my little video bench over at the side, and we've got set up over there. Let me just get this running for us. There we go. I've just got a vise and a blade out of a hacksaw, and just a normal hacksaw blade. We're kind of familiar, these are very whippy, and so we can see a simple vibration. I've just got a pink tag on the end so we can see what's going on, and we can see a simple vibration. I've got here a heavy magnet. I'll put that onto the end of the hacksaw blade, and much slower. So we've seen with vibrations that if we add weight, mass, to that, our vibration will slow down. The frequency will slow down. If I make that shorter, and we've all played with rulers in schools, sort of hitting them on the desk, I've made it shorter, the vibration speed, the frequency has gone back up. That's because it's now stiffer. Force equals mass and acceleration. So we put more mass, the acceleration is slower. We make it stiffer, more force, the vibration will go faster. So that's kind of a quick reminder for many of you. I'm sure you're all familiar with that. So here I've just got a tin can, somewhere between what Michael will be doing with the toilet roll and Anya and quantum entanglement, a simple tin can with a rubber band. And we've all sort of played with rubber bands. I'll just stretch it across the top. We get a note, it's vibrating. Like Michael, I love sound. Pull it tighter. Make it looser. A lower note. So my question to kind of get the evening started is, if I start plucking the rubber band and start stretching the rubber band out, will the note go higher, or will the note go lower, or will it do something else? What's your thoughts about that? So if I pluck the rubber band, I've got that low note. If I pluck it when I've got it pulled out, what will the note be? All right, let's try. Just move the microphone off stage so we can see that I am stretching the cable, the rubber band. All right, now probably twice as long now. Let's try that again. Twice as long. I don't think that's going much higher. I don't think that's going much lower. In fact, unless I really stretch the rubber band, that note is going to stay the same. And what's happening with this is, sure enough, as I stretch it, it's tighter. And if that was a guitar string, the note would go higher, but I'm also making it longer at the same time. And those two effects cancel out. So one is making it higher, others making it lower, it stays the same. So there's just something to try. Just get a rubber band, put it against your ear, and see what you hear. So what we'll look at now is an activity about noise cancelling headphones and just how they actually work. What I have here, just a PVC tube set up, a little bit like a trombone. On one side, I've got a small speaker, and this is all open so that the sound can flow all the way around and come out this side. Now that microphone which I bumped before, there we go. And on the phone, I've got a little frequency generator so I can make particular tones of music. So we'll put a reasonably high one on. We should hear both notes. But now we've got rid of the high one and we're left mostly just with the low note. And so we can filter those out. The sound is coming in Sound is compressions and expansions of gas. That's what we're visualizing. Coming around and meeting here and coming out to us to here. All right, so that's what's happening at the moment. But when I pull the tube out, let's go and see what happens when I stretch that tube. And now, because this wave has further to go, those pressure waves are not meeting together, they're meeting out of step with each other. So rather than having high pressure sound wave meeting, they actually miss each other and cancel out. But that's only because I've got this tuned to exactly the right frequency. One of the things which I spend a lot of time dealing with is in fact looking at environmental science and hands-on activities. And we've all heard about greenhouse gas and climate change. Here is a model that I have of carbon dioxide. And one of the reasons carbon dioxide is the greenhouse gas it is because of vibrations. And CO2 molecule vibrates very much like that at a particular frequency. And that frequency matches infrared. So infrared light, infrared radiation has a particular frequency, and CO2 vibrates at that frequency. So infrared light, infrared energy reaching the planet excites carbon dioxide in a very particular way. And that's why it picks up that energy. That energy gets translated into heat, and that's the source of greenhouse gases. I'll just very quickly do one little demonstration. We'll take my special CO2 exciting device. So we've got two of these, two CO2s, very much the same. And if I vibrate the stick at the right frequency, I'll get the CO2 to vibrate. If I just add now a little bit of weight to one of those, I'll change the frequency. So now I can get the top one to vibrate at one frequency, but the other one's not really vibrating. If I go a bit faster, I can get the bottom one to vibrate, but not the top. And so different molecules with different masses, different atoms, will vibrate at different frequencies. And that's one of the things behind our use of pH indicators, those coloured ingredients that we add to tell if something is an acid or a base, if it's alkaline. Those chemicals in an acid get protons added to them. That makes them heavier. They vibrate slower. They change their colour because of that. And if you look at all of the pH indicator charts, you'll find most of them, almost all of them, will become red at an acid. And that's because those protons are making them heavier and vibrating slower, which matches the red end of the spectrum.